Welcome physiology students to the graded and action potential workshop. We'll be looking at what a graded potential is and what an action potential is. We're just going to take about 1 or 2 minutes to focus on this first slide though. As we're looking at this is showing an action potential depolarization curve, an action potential peak, and a repolarization curve. We'll be going through the phases and you guys will be filling out these phases on your worksheet, so feel free to pause the video at any time to fill out those phases. We'll also be looking at what happens and what causes the inside of an axon to go from -70 to +30. There has to be something that changes within that axon to reach a positive charge. And it does that when a sodium voltage gated channel opens. So a sodium ion is positively charged and it will rush into an axon to cause this upswing in this depolarization curve graph. The repolarization phase is showing what happens to the inside of the axon as the cell becomes repolarized. And in this phase, potassium ion gated channels will open, and potassium is a positively charged ion and it will leave the axon or the cell. And as that positive charge leaves the cell, the inside of the cell becomes more negative again. We'll talk about why it becomes a little too negative and how we get the axon back up to what we call resting potential. This graph is showing time in milliseconds on the x-axis and membrane potential in millivolts on the y-axis. The membrane potential again refers to the electrical charge potential inside an axon or inside a neuron. And you'll see here that when a stimulus is applied to an axon, and a stimulus can be any sort of stimulus that would cause a change in the nervous system to depolarize, this action potential really only lasts a couple milliseconds. That's extremely fast for this signal to be passed down an axon. And we want it to be fast because we want our nervous system to respond quickly to changes to stimuli around us. So let's take a look and review the structure of a typical neuron. We'll start with the dendrites, which are kind of the fingers that stick out from the cell body. Dendrites will receive the signal that's being sent to this neuron from a different neuron. And these dendrites will pass that signal on to the cell body here with the nucleus in the middle. The cell body is the neuron's main integrating center. So the cell body will receive the signal, it'll integrate, process that signal, and then send it on down through the axon. And the axon is the long part of the neuron. It begins with what we call an axon hillock, which is the place right where the cell body meets up with the axon itself. And graded potentials will try to drive the axon hillock to stimulate an action potential in the axon itself. Within the axon, you see these Schwann cells, which are signified by a little circular nucleus. Schwann cells create what we call myelin sheaths that act as electrical tape that will insulate the axon and allow that electrical signal to be passed more quickly down the axon. That electrical signal actually jumps between myelin sheaths in these little spaces called the nodes of Ranvier. And then once that electrical signal gets to the axon terminals, it releases what we call neurotransmitters. You might have heard of one, acetylcholine. Other neurotransmitters are released from the axon terminal. They pass through a synaptic cleft and then bind to receptors on their target cell. Sometimes it's a muscle cell, sometimes it's another neuron. So a graded potential, the purpose of a graded potential is to drive the axon hillock to threshold in order to generate an action potential further on down an axon. But a graded potential acts a little different than an action potential. The stimulation causes ions to rush in and radiate out where that stimulus occurs. And the radiation or the spread of depolarization can occur in both directions. And that's seen here on this picture. It's polarized like a wave, and that means that these waves of stimuli can summate with other waves or quickly lose their intensity altogether. So again, the purpose of a graded potential is to drive the axon hillock threshold in order to generate an action potential in the axon itself. Here is the original active area, and you can see how graded potentials spread in either direction. This will be different from when we talk about action potentials that only travel in one direction. When we talk about depolarization, that word always has to do with a change in charge. And in this case, the inside of axons are normally more negative, so depolarizing an axon would mean an influx of positively charged ions to bring the inside, the axon, more positive. And that's what depolarization is. Here's another look at a picture of graded potentials, again showing the initial site of potential change and the direction of current flow from the initial site, again flowing in each direction. Okay, I include this picture in here as well to show then in an axon how an action potential is generated. And it all has to do with voltage-gated ion channels opening and closing for sodium and potassium. And normally sodium has a greater concentration outside of the cell. So these three steps are just showing how depolarization of an axon occurs. When sodium ion channels open, sodium will rush down its electrochemical gradient inside the cell. And remember, inside an axon is normally at -70. So when positively charged sodium ions rush in, that will bring that deflection curve more positive. So your membrane potential will become more positive, and we'll start to see an upswing in your action potential graph. The charge will spread, and the membrane downstream will also depolarize. We have kind of sort of this positive feedback mechanism. Once we reach what we call threshold, once the inside of the cell gets to at least -50 or -55 millivolts, we have a positive feedback mechanism that starts to open up automatically more and more sodium channels. So that sodium channels will start to open automatically. Sodium ions will rush into the cell, further causing this upswing in depolarization and eventually leading to an action potential peak. This is showing action potential propagation. Here is the signal traveling from the dendrites through the cell body and down the axon. And we've kind of focused in on these two sections of the axon, showing how sodium channels will rush into the cell and get into the cell to threshold. And as sodium channels rush into the cell, they'll make the inside of the cell more positive. And that's where we get to when it says depolarization, threshold rising, and the action potential peak. After the action potential peak, the inside of the cell becomes more negative when potassium channels open. And potassium channels have a greater concentration inside the cell than out. So when your potassium channels open, they're also positively charged. They will travel outside the cell, and that's our second voltage-gated ion channel that will open. When potassium ions leave the cell, that causes repolarization of the inside of the cell. Repolarizing means positive charges are leaving, so the inside of the cell will become more negative again. We'll talk about what hyperpolarizing means because your potassium channels remain open for a little bit longer than normal, leading to kind of in this extra negative state or phase in the graph. So a little more between graded potentials and action potentials, just another review. The amplitude depends on the strength of the stimulus in the graded potential. And in action potential, the amplitude is all or none. And what that refers to is once enough sodium ions enter the cell to increase the membrane potential to at least that threshold amount, we will get an all or none response. So once we reach threshold, we'll get an action potential peak no matter what. And that's due to this positive feedback opening up more and more sodium channels as it travels. The stimulation of a graded potential requires very little stimulation. An action potential, however, in order to get an action potential, we need at least 15 to 20 millivolts of change. And that's the difference to go from -70, our normal resting membrane potential, to -55. The summation in a graded potential, stimuli strengths can summate in waves, but in action potential, we only get one potential at a time, and that's what happens during the refractory period. Once your potassium channels remain open for a little bit longer than they should, all your sodium channels have closed. And that hyperpolarization stage, because your sodium channels are closed and the cell is hyperpolarized, we cannot generate more than one potential at a time. The spread of a graded potential decays with distance. It's very short-lived, and an action potential is more regenerated and longer-lived. The origin of a graded potential arises in dendrites and cell bodies, again, because the purpose of it is to trigger an action potential in the axon hillock, and an action potential arises at trigger zones and propagates down along an axon. Graded potentials can use chemical, mechanical, or light channels, whereas an action potential uses those voltage-gated ion channels, specifically sodium and potassium. A little bit more about action potentials, and I'm going to encourage you guys to maybe pause the video right here and take a look at some of your application questions, which have a little bit to do with what we'll talk about now. The all or none and positive feedback mechanism has to do with once your sodium channels close, it takes about 1 to 2 milliseconds for them to open again. So this kind of halts any sort of more action potentials from being generated. We call this the refractory period. So your action potential is unidirectional. It only travels one way down an axon. That all or none response refers to the inside of the cell, the membrane potential reaching threshold. Once the inside of the cell reaches threshold, enough sodium ions have entered it, we get a positive feedback mechanism where we'll generate an action potential no matter what, and all sodium channels will open. And then hyperpolarization again refers to when potassium voltage-gated channels, they open a little bit slower and they stay open longer than sodium channels. So remember, potassium channels were open during the repolarization phase as the cell was becoming more negative. And because they stay open a little bit longer, the cell will kind of dip into this hyperpolarization phase. So this, again, is a look at the propagation of an action potential. And we'll start here, kind of the remainder of the axon still at rest. And we'll start kind of traveling right to left as we look at this graph. So at the bottom, we see a membrane potential of -70, and there must have been a stimulus applied right here because our -70 millivolts is starting to increase. So we know that sodium channels have opened from the stimuli being present, and sodium ions are entering the cell. It has reached threshold at this point, -50, so we get an all or none response where more sodium channels are being open at this point. So the millivolts will continue to rise until we get to about +30, where that action potential peak occurs. And you can see that here above, how sodium ions are rushing into the cell, making it more positive. So we get a more positive upswing in our graph. Then we get to the repolarization phase where the graph starts to dip down and become more negative, and that's because positively charged potassium channels are leaving through potassium voltage-gated channels at this point. So because positive charges are leaving the cell, the inside of the cell becomes more negative, and like we said before, potassium channels stay open a little longer than they should, so we get down into an almost hyperpolarization phase. And we'll talk about how we can go from hyperpolarization back up to resting state. And we'll talk about that right now with this graph. So you can see here a stimulus has been applied. I'm going to have you guys pause the video recording again to fill out the phases in your worksheet. You can also begin to fill out what happens at each phase and what channels are opening and closing. So once a stimulus has been applied to an axon at resting membrane potential, these are showing failed initiations, but once we get a stimulus that reaches the inside of the axon to threshold, so again, enough sodium ions have entered, we get our action potential peak, then the potassium channels will open potassium rushes out of the cell, so we get a repolarization. And then this refractory period is caused when those potassium channels remain open a little bit longer than they should. And to get back up to resting state, we have what we call the sodium-potassium pump, which transports 2 potassium back into the cell and 3 sodiums back out of the cell to try to establish a concentration gradient that should exist with more sodium ions concentrated outside of the cell and more potassium ions concentrated inside the cell. And I include this picture as well to take you through your worksheet. You'll have to fill out what happens at each voltage gated channel. And it has you draw and label the inside of the cell and the outside of the cell and what happens at each phase in this graph. Which ions are moving? Are they moving in or out of the cell during resting phase, depolarization, repolarization, and long-term active transport? So during the resting phase, no channels are open at any point because the cell is resting, no stimulus has been applied. Then during the depolarization phase from a stimulus, we have the voltage-gated sodium channels opening. Potassium channels are closed at this point. So sodium channels are opening and sodium rushes into the cell. We reach threshold, positive feedback, we get an action potential peak right at the top. Then during the repolarization phase, potassium channels open and potassium travels down its electrochemical gradient to the outside of the cell. Potassium leaves the cell. When the potassium charges leave the cell will become more negative because potassium is a positively charged ion. And this, the graph doesn't label it here, but this is your hyperpolarization phase. And then long-term active transport refers to that sodium-potassium pump that tries to reestablish the gradient of having a higher concentration of potassium inside the cell and sodium outside the cell. So this is an active transport process, the sodium-potassium pump. It transports 3 sodium out of the cell for every 2 potassium it transports in the cell. This is an active transport process, so it requires ATP for that. And that's the end. I hope you guys are all doing well. Thanks for listening.